The title of my today's talk is Realization of Innovative Light Energy Conversion Materials Utilizing the Supercomputer Fugaku, which is our project name in the Fugaku Promoting Project. As you know, before the production run of the supercomputer Fugaku, we carried out the FS2020 project. And as a part of the FS2020 project, 9 priority issues toward the effective use of Fugaku were selected from various research fields, and the target software programs were developed. And among 9 priority issues, we carried out the project on development of new fundamental technologies for highly efficient energy creation, conversion, and storage and use. And in this issue, 4 application programs were selected as infrastructure programs that effectively use Fugaku to contribute solutions to renewable energy problem. And among 4 programs, LTChem and GERAN were quantum chemistry program, and Modulus is a general purpose large-scale molecular dynamics program, and STAT-CPMD is the first principles plane wave program. And these 4 programs have been optimized to make full use of the massively parallel computing power of the supercomputer K and Fugaku. Okay, let me introduce our developing LTChem briefly. LTChem is a high-performance software package for molecular electron structure calculations for general purpose on various supercomputers and in-house workstations. Specifically, LTChem is designed to carry out high-performance calculations on computers with tens of thousands of nodes for grand and excited state density functional theory DFT method, and the second order perturbative Miller process MP2 method, and the quantum Monte Carlo method. For example, we developed an efficient parallel algorithm for MP2 calculations and could perform better parallel scaling calculations with our new algorithm on the supercomputers K and Fugaku. When we use almost full node of the K computer, and the computation time for this kind of nanographene with almost 10,000 atomic orbitals was only 11 minutes with our new MP2 algorithm. As a result, we achieved the world's largest wave function-based electron correlation calculation. And currently, we are developing a new version of LTChem. It adopts a memory-distributed space matrix algorithm based on LT-Poly library to overcome available memory sizes per computer node. And our new version also adopts an algorithm with regular communication patterns that map to high-dimensional torus network architectures to manage significant irregular data movement. To this end, the new version of our LTChem was capable of calculating molecules with 10,000 atomic on the K computer. Therefore, I hope LTChem will realize our initial quantum chemistry calculation for realistic molecules, including 100,000 to 1 million atoms, such as a whole photosystem 2 on the supercomputer Fugaku. Currently, the successor to the priority issues of the FS2020 project are named the Program for Promoting Research on the Supercomputer Fugaku is in progress and includes the 22 selected projects. Among the 22 projects are the successor to our previous issue on energy-related materials in the FS2020 project. We are currently working on a project on light energy conversion materials from last September. In our project, we aim to realize the social implementation of innovative light energy conversion materials using massive materials simulations and informatics on Fugaku. Specifically, we would like to realize hydrogen generating photocatalyst with the world's highest conversion efficiency of over 10% in collaboration with industry. And we would also like to social implement the photocatalysts that inactivate infectious virus and selectively and effectively generate hydrogen peroxide for disinfection. In addition, we would like to realize lead-free perovskite solar cells with a conversion efficiency of over 30%, surpassing silicon-based solar cells. In most of our recent projects, including the Fugaku promoting project, we are interested in material designs, not only by simulation, but also by materials informatics. We would like to realize accelerating the discovery of novel materials such as photovoltaics, photocatalysts, polymer batteries, and advanced biopolymers by establishing novel materials informatics techniques that simulate large databases and mathematics in material science with high throughput simulation on the Fugaku supercomputer. Furthermore, we have several plans to collaborate with experimental groups and industries to discover new materials that are highly efficient, low cost, environmentally clean, and sustainable. Here we would like to realize novel material designed by co-designing experiments, theorizing, simulation, and informatics. Okay, today I will present several of our recent activities on material design. In particular, let me introduce the material design of perovskite solar cell. And the perovskite with small organic molecules are one of the promising new generation solar cells, and the most prominent perovskite in photovoltaic application is a type of perovskite containing lead atom. However, the lead is toxic, so it is desirable to design and implement materials for lead-free perovskite solar cells. In our previous study, to search for novel lead-free perovskite solar cells containing non-toxic and wide available metal, we performed a systematic high-throughput first principle simulation on the K computer for over 11,000 compositions of perovskite. By applying the screening procedures to all the computed compounds, we discovered novel candidates for environmentally friendly lead-free perovskite solar cells and proposed 51 low-toxic halide perovskite, most of which are proposed newly in our work. We also found that the potential candidates are categorized as only 6 types based on the combination of groups to which 2 metal elements belong in the periodic table. Based on this achievement, in our Fugaku promoting research project, we plan to perform more massively high-throughput simulations for a huge number of compounds totaling more than 10 million, employing a comprehensive combination of elements with a higher degree of freedom than our previous research to build a large-scale material database for perovskite solar cells. Then we will propose candidates for lead-free perovskite solar cells through the efficient search with screening and demonstrate novel materials by providing the obtained results to the cooperative experimental research group and the related companies. The future of our project is to design novel materials, not only by simulation, but also the material informatics. And we will construct a prediction model to estimate both conversion efficiency and stability through the machine learning based on the material database constructed by the simulation to propose a candidate for highly efficient and stable lead-free perovskite solar cell. Okay, next I will present our previous works on the materials informatics, which are applicable to our Fugaku promoting research. In this study, we discovered new whole transport materials for perovskite solar cells, which can be alternatives to non-spiral OME TAD by using materials informatics and simulations. Spiral OME TAD is the most frequently used whole transport materials for perovskite solar cells. However, the spiral OME TAD and its derivatives are expensive because of their multi-step synthesis and low yield. Thus, we would like to discover novel candidates for whole transport materials that yield high conversion efficiencies and are easier to synthesize than spiral OME TAD. I will introduce the detail of our approach. First, we collected experimental data for power conversion efficiencies of perovskite solar cells, which include 88 perovskite with valence band maximum and conduction band minimum, 326 whole transporting materials, 10 electron transporting materials with conduction band minimum, 10 dopant, 28 codopant, and 50 active areas. Consequently, the total number of our data set is 712. The second step is to prepare the candidate molecules and the fragment. In this step, every whole transporting material in our database was decomposed to 3 fragments. Then the new compositions for the whole transporting materials were built by the combination 3 fragments selected from the prepared fragment set. And to construct the machine learning model, we need to evaluate molecular descriptions. In our approach, the topological and geometrical molecular descriptors for each fragment were calculated by the modulet library, while the quantum chemical electronic descriptors for each fragment were evaluated by our RIKEN, which include HOMO, LUMO, total energy, dispersion energy, electronic energy, heat of formation, and dipole moment. The next step is to predict a candidate for whole transporting materials. And to predict the whole transporting materials with the highest power conversion efficiency, we adopt a prediction scheme with the Gaussian process regression model, which is known as Bayesian optimization. And the Bayesian optimization improves the uncertainty and predictability by considering the error variant of the prediction values. And to construct this Gaussian progress regression model, the classical and quantum molecular descriptor as well as experimental parameters are provided as input, while the power conversion efficiencies with error variant and predicted as the output from the Gaussian progress regression model. Then to obtain the optimal set of fragments which compose the candidate molecules, that the equation function obtained from the Gaussian progress regression model was optimized by particle swamp optimization, which can tackle the optimization problem in the vast chemical space, where the number of all compositions is over 90 million in the study. And the most distinctive feature of our study is to perform the virtual experiment using the different prediction model rather than the Gaussian process regression model. That is, the power conversion efficiencies of whole transporting materials proposed by the Gaussian process regression model were determined by the deep neural network model. And the prediction value obtained from the deep neural network model was added as an input for the Gaussian process regression model. As a result, both Gaussian process regression and deep neural network models were reconstructed by repeating the prediction and the virtual experiment so that the whole transport material with the highest power conversion efficiency was selected by the improved model in every step. This slide explains the detail of the construction of the deep neural network model. And for construction of the deep neural network model, similar to the construction of the Gaussian process regression model, the classical quantum molecular descriptors and the experimental conditions are provided as inputs, and the power conversion efficiencies are predicted as outputs. The ingenious point is that to construct the accurate deep neural network model, 3 prediction models, including partial least squared regression, support vector machine, k nearest neighbors were prebuilt, and the prediction values for power conversion efficiencies were added to the input for the deep neural network model. Okay, today I will show you only the final result. And after we carried out 20 independent virtual experiments with 100 update params, we have successfully identified 2 novel candidates for whole transporting materials of perovskite solar cells that yield high conversion efficiencies and are considered to be easier to synthesize than spiral emitters. Okay, well, that was the end of my talk. Thank you for your listening.